Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Lord, thank you for these students. Just pray with us today. Help us to just wrap up our thinking about differential equations for this course. And I just pray that you just bless this class, Lord. In your name I pray. Amen. Oh, we can leave that door open because otherwise 1,000 degrees in here. Hopefully, well, who knows? Every once in a while we may have a break from lecture and get to listen to a conversation in the hallway. It's always fun. All right, so I want to talk to you guys about, additional distractions, but again, I think it's worth it. So we're still in section 9.3. Now there's the second order constant coefficient ODE problem. So there is still some unfinished business left for us in the earlier sections, and in particular, I need to tell you guys a few things about orthogonal trajectories, and hopefully I'll have some time for your homework questions at the end of class today. But I need to wrap up the big picture of how we solve these second-order constant coefficient ODEs. And so I think the next order of business, last time we already have seen what? We've seen that if you look at ay prime prime plus by prime plus cy equals to 0, if this is the equation we're trying to solve, right? Call this thing star. What we argued last time is we noted if we set y equals to e to the lambda x, then this is a solution, then the function e to the lambda x is a solution to star, right? If a lambda squared plus b lambda plus c is equal to 0. This equation, so what we did in making this guess, it's really kind of fantastic. We traded a differential equation, right, up here. Through this guess, we traded the differential equation for the problem of what? This is a differential equation, right? So its solutions are functions, whereas this is a algebraic equation, right? A quadratic equation. In fact, we know how to solve that, either by factoring or completing the square, or worst comes to it, quadratic formula, right? And I showed you, for example, that we looked at the example y prime prime plus 3y prime plus 2y equal to 0. We saw that e to the minus x and e to the minus 2x were solutions, right? So you start thinking about it, okay, well that's the case that the quadratic equation has distinct real roots. What if it has a repeated root? Right, so you can kind of think backwards and think, okay, so, what would it be? What would be a case I could investigate? Intuitively speaking, if you think about it, let's see here, to get a repeated root, what's the simplest repeated root you could think about for a quadratic equation? How about y equals x squared? Isn't that the first thing you study? So you have a repeated root of 0. We all know the graph of that, right? So if you think backwards, right, lambda squared equals to 0 has repeated, this corresponds to repeated root 0, right? So if there's any justice, there shouldn't be much difference between a repeated root of 0 and a repeated root of 3 or something like that, right? So if we can see how the repeated root of 0 works, maybe we can just from that cipher what the solution should be if, say, this has repeated root like 3 or something. Okay, so I'm going to draw a parallel here, and we're going to make an analogy, and we're going to make a guess. So this would be repeated root 0. What would be repeated root 3 would be something like lambda squared equals to 9, right? Oh, I'm sorry. No, that wouldn't be it at all, would it? Why would we get a repeated root of 3? That would be plus or minus 3, right? So I have to do like this. Lambda minus 3, quantity squared equals to 0. That would be the equation which has a repeated solution of 3. This one, which is the same as what? Lambda squared minus 6 lambda plus 9, right? Equal to 0. So continuing to work backwards, which differential equation did this come from? How would you get to this from one of these. In other words, which differential equation has lambda squared equals to 0 as its, by the way, this is the characteristic equation. That's its name. Can you guys tell me? I'll do the harder one over here. This would come from differential equation y prime prime minus 6y prime plus 9y equals to 0. If I faced that second order differential equation, I would get the characteristic equation right above it. Thinking backwards. So what's the differential equation for this one? Right? Can we solve this differential equation? Yes, we can. You can solve that just by direct integration, right? Because this, if you integrate once, we get y prime is equal to c2, all right? And if I integrate one more time, what do I get? I get y is equal to c1 plus c2 times x. Do you agree? So let me write this somewhat suspiciously. So if you tilt your head and squint, you can see that this is really y of x is equal to c1 e to the 0 times x plus c2 x times e to the 0 times x, right? You have to use your imagination, but it's there, right? E to the 0 is 1. And then over here, what do we already know from like last time? We already know that we already know that this has y equals to e to the 3x as a solution. We proved that would work last time, right? Well, on the basis of this example, what do you guess the solution might look like with two things here? So I'll do the easy part. C1 e to the 3x. What's the other piece? C2 what? What goes over here? Exactly. By analogy, right? And that's the way it works in the repeated root case. In the repeated root case, we take e to the 3x as one of the fundamental solutions, and then x e to the root is the other fundamental solution. And that turns out to be the general solution for this example here. If you want me to show it works in general, we can make a substitution. You could start with like what's a general, y prime prime, what's repeated root case look like? It's y prime prime plus how's it go? 2 times the root y prime plus r squared y equals to 0. This would be a generic repeated root case, right? Because that gives you like, I'm sorry, I need a minus here. So to work this out in general, you have like lambda squared minus 2r plus r squared equals to 0, which would be lambda minus r quantity squared equals to 0. And to show that, to derive this thing in general, what I do is I just make a substitution. I say, okay, well, I'm going to let z equal to, how's it go? I think it's y. No. Oh, I can't remember right off the top of my head. It doesn't really matter. Here, let me give you a less sophisticated proof of it. Oh, I shouldn't have erased that. Curses. So here's the general one, minus 2r y prime plus r squared y. If we let y equals to x e to the rx, you can show that is a solution to the differential equation above, right? And how would we do that? It's really more of a theorem. This differential equation has solution, right? How do you prove that theorem? Very simple. We just differentiate. Y prime is what? Differentiated product. What do we get? xr e to the rx, right? And then I can clean that up a bit. That's 1 plus Rx times e to the Rx, right? Differentiate one more time. Y prime prime is equal to R e to the Rx plus 1 plus Rx times R e to the Rx. Clean that up. We've got ourselves a 2R plus what? XR squared e to the Rx. So what am I? I'm just differentiating. Why am I doing that? I want to show you that x times e to the Rx is in fact a solution. So we guessed that this is true by analogy, right? I'm just showing you it's true for anyone by just direct calculation. So what does it take to show that this is a solution? I need to plug it back into the differential equation, which is not a differential equation yet, is it? You guys, come on. You gotta stop me. This is equal to 0, right? Otherwise I don't know what that is. It's an expression, I suppose. Let's call this thing star, right? Okay, so what do we look at? We look at y prime prime minus 2r y prime plus r squared y. What's that equal to? Well, there's my y prime prime, right? Minus 2 times r times what's my y prime? Right here, right? 1 plus Rx e to the Rx. And then what's left? Plus r squared y, which was what? X e to the Rx. And then you just got to look at it, right? Like, check out what happens here. I have got what? I've got an xr squared here, right? I've got another xr squared term over here. So I have 2 xr squareds. Where else is there xr? How about here? Minus 2r times rx. So I get plus 2, I get minus 2 of those terms. Gone, right? They cancel. What else are we left with? How about this 2r? What balances out this term? That's minus 2r, right? So that's balanced by this guy. And that's everything. So that proves for you, in general, that if you have a repeated root, the solution x e to the root x is a solution. So we settled that, right? Yes, sir?
How do we notice that y equal to x e to the Rx again?
What's that?
Like, how do we notice that y?
Over here. We investigate what we can already do, which is second derivative of the 0 case. That led us to observe that we multiplied by x here. It wasn't my idea. One of you guys said I should put an x here. Did you read the book? Yes. Sorry, I don't usually rejoice about students not reading the book, but in this particular case I do, because my point is, if you understand this and you just make a guess, you can see that it should be multiplication by x that gets you the next thing. It is a deep and interesting question why this is true in general. I know at least 7 different answers, which I talk about in the differential equations course. But to me, it's a very fascinating issue why there's an x there. I don't think it's at all intuitive. I just cheated you guys to make you think you could guess it. You can also make a substitution, like y is, I forget the substitution. There's a substitution you can make to that differential equation, which converts it to like z prime prime equal to 0. You integrate it twice, and then you get back. It's possible to calculate it directly like that. I was trying to think of it. I couldn't think of the substitution. It's really simple. I'm going to kick myself after class for not remembering it, but we must go on. What's the other case? So let's start making a compendium of results over here. So there's a big theorem, basically how to solve ay prime prime plus by prime plus cy equals to 0. So here's what we do. We write the characteristic equation and find its roots say, lambda 1 and lambda 2. Then there are three cases. Case number 1, lambda 1 not equal to lambda 2, both real. Then we get y1 is equal to e to the lambda 1x, y2 is equal to e to the lambda 2x. All right? Step number 2 we just worked out. If lambda 1 is equal to lambda 2, and we'll just say it's equal to lambda in that case because we don't need subscripts if we just got one lambda, right? Then y1 equals to e to the lambda x, and y2 equals to x e to the lambda x are solutions to star, which I will label shortly. What's the other possibility? Excuse me. What's the other possibility? Quadratic equation, you got three cases, right? Bounces off the real axis, cuts through the real axis two places, never hits the real axis at all if you think about y equals to a quadratic, right? That third case is the complex case, right? You could have complex solutions. So step 3 would be lambda 1 equals to, say, alpha plus I beta, and lambda 2 is equal to alpha minus I beta. And this is here, alpha and beta are real numbers, and we're assuming beta is not equal to 0. That's the third case. So what is y1 and y2 in that case? I'm going to show you something, okay? What would it be natural? What would be natural is we looked at e to the lambda x, right? And I argued that y prime was lambda e to lambda x, right? And y prime prime was lambda squared e to lambda x by the chain rule last time, right? That was the heart of our derivation of the characteristic equation as a necessary consequence. You can ask the question, wait a second, hold on a second. I didn't know that lambda could be complex. You didn't say lambda was complex last class. I didn't say it wasn't. I said lambda was a constant. I was careful to say that. I never said lambda was real. Don't put those words in my mouth. And that was on purpose, because, in fact, this still makes sense when lambda is complex. What does this mean if lambda is complex? If lambda is equal to alpha plus I beta, what is this? This is e to the alpha plus I beta times x. And I'm here to tell you that still makes sense. And it makes sense in the most natural way possible. A simple extension of what I already told you about imaginary exponentials. Here's how it goes. This is e to the what? Alpha x times e to the I beta x. That is how we define e to the lambda x, given that we already know what e to the I beta x is, right? If you don't like that, you could take the definition to be the next line. The definition is e to the alpha x times cosine beta x plus I sine beta x. You can prove that, and so how do you differentiate? Let me just quick course here. If I have the derivative with respect to x of something like 3x squared plus I times x cubed, the way it works, the definition of how to differentiate things like this is you differentiate the real and the imaginary parts separately. So what you do is you do like d dx of 3x squared plus I times d dx of x cubed. This is how we differentiate something like this. So we get like 6x plus 3i x squared. I mean, I could summarize how you differentiate complex valued functions of a real variable very simply. Basically, we set d dx of I equals to 0 and proceed naturally. if you want a formal definition, here it is. The definition, if I differentiate with respect to x, u plus iv, where u and v are functions of x, the definition is just du dx plus I times dv dx. This is how we differentiate complex valued functions of a real variable. Technically speaking, this is like week 2 or 3 in Calculus 3. But this is not the part of Calculus 3 anybody has a problem with. We learned that if you want to differentiate a vector of functions of a real variable, you just differentiate each component in the vector separately. Some of you are taking physics right now. We're using that in there anyway, right? There are calculus curriculums which put that in Calculus 1 with good reason. Now, I will not force you to watch me prove. So there's a hole, right, to fill, which is, it's not at all obvious now, right? Look at this. It's not at all obvious why. Oh my goodness, what have I done? I somehow, somebody's listening on headphones right now. That would have been painful. Here. Well, I mean, not right now. It's a live stream. It'd be ridiculous. Let's see here. Let's see here. So, think about what it means then. I told you that the derivative of e to the lambda x was lambda e to the lambda x, right? And you believe me because you know the real case, right? But to say that that's also true for the complex case says a lot now, doesn't it? Think about what it says. See what it says? This is e to the alpha x cosine beta x plus I e to the alpha x sine beta x. So this is like the u, and this is like the v in this definition over here. So I'm telling you the derivative with respect to x, even in the complex case of e to the lambda x, is still lambda e to the lambda x. That's no longer obvious. That's not something you've proved before, probably. I doubt you've proved that before. Let me show you why it's true. It is in my chapter 16 here. I have it in gory detail. Don't worry, it won't be too violent. Let's see here. Where do we go? Eventually, we'll get past all this first order stuff. All right, second order. Here it is, in glorious detail. So to differentiate e to the lambda x is to differentiate that, which is to differentiate both of these things separately, right? But both of these, you got to do the product rule on, and the chain rule, right? You pull down an alpha when you differentiate this. You pull out a beta when you differentiate that, and likewise for these, which gives you this and this and this and this. Then you group all the alpha stuff together. Well, you can factor out an alpha plus I beta here, and you can factor out a minus alpha, minus I alpha minus beta from the sign terms, right? But then you can factor out alpha plus I beta on both, and then you have this. But this is exactly e to the lambda x again. So it's a combination of the product rule and the chain rule applied to products of sines and exponentials. It's all in there. But it's true. So we can use it. So the derivation I showed you last time still works, which means we have two solutions. All right. But what's the rub? Let me put this away. Oh, I hope there wasn't a question. Sorry. Oops. I'll try to be brief. I'm just trying to show you guys why it works at the moment. So let's see here, an actual example, something like this. Y prime prime plus 4y prime plus 5y equals to 0. All right. So what we have is a characteristic equation, lambda squared plus 4 lambda plus 5 equals to 0. Completing the square is where it's at. We should complete the square. This is lambda plus 2, quantity squared, plus 1. So, by the way, in this case, the characteristic equation can be rewritten like this. Lambda minus alpha squared plus beta squared equals to 0. Assuming that I have a equals to 1, the characteristic equation just looks like that. That's what happens. And so once I have this format, I don't have to solve the quadratic equation or anything like that. I can directly read from this expression the complex root. Alpha equals what, beta equals what from this? Beta equals what? Now you could say, well, beta could be minus 1. Fair enough. Just choose the positive one. Don't make your life hard. You could go plus or minus on the beta, that's true. But this will work. And so what we have is we have y is equal to e to the minus 2x. Well, let me write it out here. E to the minus 2 plus I times x, right? But when we multiply that out, what that is e to the minus 2x cosine x plus I e to the minus 2x sine x. But by the way, we need two solutions, right? That's the general theorem, is that the general solution to star has two what are called linearly independent solutions, two independent solutions. It was these guys in the first case, right? These were independent solutions. This and this are independent solutions. If you look at their graphs are not the same shape, all right? Those are independent. That's what kind of solution is that? We're looking for real solutions, by the way, right? So this is not a real solution. This is a complex solution. How do you get real solutions from this? Here's a theorem. If a z prime prime plus b z prime plus c z is equal to 0, and z is equal to, say, y1 plus I y2, then a y1 prime prime plus b y1 prime plus c y1 equals to 0, and the same for 2. In other words, what? That is to say, the real part of z and the imaginary part of z, which, by the way, are y1, and the imaginary part in my notation would be y2, are both real solutions to star. And in fact, they have to be independent solutions, because the one has sine and the other has cosine. So that means that they're not the same thing, basically. Yes, sir.
For something of z equals y, I can't make out what that says.
And
It says that is comma, and then what did you write?
I'm trying to write like R-E-Z, and then I-M. So that's a real part and imaginary part. It's just... I won't subject you to the proof of this. It's just like what I showed you last time for the sum of solutions being a solution, same calculation. Just it goes through the red definition over there. What I just want you to know is that for this example, what do we get? What are the two real solutions we get from this in view of the theorem? Y1 is what? 2x cosine x, right? And y2 is sine x. And so that's the end of the story here. If we have a complex solution, then y1 is equal to e to the alpha x cosine beta x, and y2 is equal to e to the alpha x sine beta x. And then the conclusion here is the general solution is always of the form what? Y equals to c1y1 plus c2y2 is the general solution to star, where y1 and y2 are constructed as listed above. In the notes I was just posting to you, I call this the recipe. I mean, it's a cookbook. There are 3 cases, and you proceed accordingly. I've showed you why it's true, but I won't hold you responsible to showing why it's true, okay? This is not some, I'm not holding you responsible for the proof of these things. You have enough on your plate. You'll be plenty busy with sequences on the next test. You don't want me to ask you to prove these things. I'll leave that to the differential equations course, but I wanted to show you why these things are true because I think it's important to see why they're true. So let's work a few more examples, and then we'll go on. If there aren't questions. Of course, if you want to, if you don't believe me, if you say you're doing all this hocus pocus nonsense, complex exponential garbage, I mean, that's your prerogative if you want to say that, then it's up to you. All right? Burden of proof is on you. I already gave proof. You can go up into here. You can take these, right? And you can plug them back in to that differential equation and show that they solve it. And you'll have to do the product rule on the exponential times sine and the exponential times cosine. And it's nasty, right? All of those things are just rolled into this wonderful identity in the complex notation, lambda e to lambda x. It's so precious. We don't make things easier by not teaching complex. We make them harder, believe it or not. Well, maybe you don't believe me yet. So here's another example. Y prime prime. You guys give me anything, actually. It doesn't matter. You pick your favorite one. Y prime prime plus what? All right. You think about it. Tell me the next one. Minus 2y prime plus y equals to 0. I'll do a few of these. How about y prime prime plus, I don't know, 5y prime plus 6y equal to 0. Let's see here. I need another one. Y prime prime plus 16y. Okay, how do we solve these? Step 1. Write out the characteristic equation, lambda squared minus, in this case, 2 lambda plus 1, which is what? That's lambda minus 1 quantity squared. This one, lambda squared plus 5 lambda plus 6. Notice that there's no lambda with the y, only with the y prime, right? That's a common beginner's mistake, is to put a lambda on the y term. That doesn't belong there because there's no derivative with the y, right? And the lambda came from differentiation, remember? This factors because I wanted it to factor, and that's why I made this example up. See, sorry, not a very real-world example, but you'll forgive me. And this one is what? Right. So we can, now that we've factored the quadratics, or this one, the last one, can you complete the square on that? Well, it's already complete, right? What's the data here? So this has lambda 1 equal to lambda 2 equal to 1. So therefore, the general solution is c1 e to the x plus c2 x e to the x by the recipe. I don't even care if you say by the recipe or not. I just want you to understand that that's the solution as relates to that. Okay? Your sole responsibility here really is understanding what I wrote on that board and applying it to problems. Okay? I said a lot of things to try to justify that. I'm freeing you of those things right now. Okay? Yeah.
So how do you know the lambda 1 equals lambda 2?
Oh, because I have lambda minus 1 squared equal to 0, so I can see that the root of this quadratic equation is 1. How about this one? What's lambda? Lambda 1 equals what, and lambda 2 equals what here? Right. Is there another answer you could have given me? You could just as well have said lambda 1 equals minus 3 and lambda 2 equals. I mean, the ordering is not written in stone. That's a matter of your choice. You're choosing. Excuse me. Therefore, by the recipe, we get what? E to the minus 2x, right? Plus c2 e to the minus 3x. Oh, I put the x up in the top one. What are you asking me? Why would there be an x there? I didn't say that there's always an x on the second one. Only in the repeated root case. I mean, if I said that, I was wrong. I shouldn't have said that. I don't think I said that. Only in the repeated root case is there an x. In the distinct root case, it's just this and this. The x is special to the repeated root case. There's something weird and different about that case. I guess you could say there's something weird and different about the complex case too if you want, but I guess you're just keeping it real. Let's see here. Now this, you can cipher that alpha is equal to 0 and beta is equal to 4. Now, of course, you could also do it like this. This is lambda squared equals minus 16, right? So lambda is equal to plus or minus 4i. I mean, that's not, you could think of it that way if you wanted to. So you can see, of course, alpha is equal to 0, right? And we just choose plus beta. We choose the plus 4 for our convenience. So that tells me what? Y is equal to c1 e to the 0 times x cosine of 4x plus c2 e to the 0 times x sine of 4x. Now, of course, that would be a very silly way to write the solution. We'll write it this way instead. c1 cosine of 4x plus c2 sine of 4x. There's the general solution. This is called, well, this physically, somebody asked me last class in the other section, I can't really understand this. I mean, well, they didn't say that. He's like, could you show some applications of this? I think it would make more sense to me if you showed some applications of this. Like, I don't really think that's true, but okay, I'll humor you. I didn't say that. I thought it though. I hope he doesn't watch this. Now I'm in trouble. Just kidding. So I showed him there's two central applications that come to things like this. The one is, of course, if you take a spring, right, and you put a mass on it, and you stick the whole thing in Jell-O, J-E-L-L-O. Oh, a long shadow is cast over Jell-O these days, and pudding pops in general. Sorry, that may be too old for you guys. You can write the Newton's second law, ma is equal to minus kx minus beta v. So the minus kx is a spring force, so spring constant k. The Jell-O has coefficient of damping beta. This is a simple model for a spring, a mass under a spring force with a velocity-dependent friction force. If you rewrite this, of course, the acceleration is equal to v prime, right? So what you really got, which is, by the way, x prime prime. So what you really got here is mx prime prime plus beta x prime plus kx is equal to 0, right? Or in our current terminology, you could use y instead of x, and then you'd see it for what it is, right? Here the prime denotes time. So like, for example, this right here, if you look at it, x prime prime plus 16x equals to 0, has solution x of t is like c1 cosine of 4t plus c2 sine of 4t. That is the so-called, this is a spring without friction. And the solution illustrates what's called simple harmonic motion. if there is friction, right, if there is friction, you could have something like this, x prime prime plus, I don't know, 10x prime plus 26. So here I have a mass of 1, a spring coefficient, a damping coefficient of 10, and a spring constant of 26. You complete the square on this, you've got lambda plus 5 quantity squared plus 1 equals to 0. Because sorry, I'm skipping a step there, but lambda squared plus 10 lambda plus 26, that's lambda plus 5 quantity squared. That brings out a 25. 26 is 25 plus 1. And so the general solution looks something like this. X of t is equal to c1 e to the minus 5t cosine t plus c2 e to the minus 5t sine t. This is called weak damping. Okay. So this is a spring this is damped motion. If you can rewrite this as something like an amplitude times e to the minus 5t times, say, the sine of t plus some phase angle phi. That's just algebra. And so the solution actually looks something like this. There's like this exponential envelope here. And so what you got is something that looks, roughly speaking, like this. And it just to 0 after a while. And the same thing happens in the repeated root cases, what's called critical damping for the spring mass system. So anyway, there's an application. I don't require you to know springs. This is differential equations where we cover this and we test on it. Or later this semester in 231 for me. Sometimes Combordis covers it too. I'm not sure about Mr. Omni. So, any questions? I can make a similar comment for RLC circuits. There's a direct analog between this and a circuit with resistance, capacitance, and inductance. Maybe I'll talk about that some other day, but for the time that remains, let me talk to you about the orthogonal trajectories. And since I didn't have enough time for you guys to ask about homework, I'll push the homework back one day so I'll collect it Tuesday instead of Monday. And hey, I saw that. Don't be so happy. I'm just kidding. I would do the same. So you'll still have some time to ask me questions about this stuff Monday. How about that? Heaven knows you need to work on your homework. Oh my goodness. This comment brought to you by me grading the test. Let's see here. Golly. Oh, let's not talk about that. I'm about halfway through the grading of the test at the moment. Let me just not say anything. So check this out. If I wanted a differential equation, right, that always had solutions, right, that, say, had y increasing when y was greater than 2, and suppose you want solutions which increase for y greater than 2, and they decrease for y less than 2. Well, if you think about what function does this? How about this? How about the function y minus 2? Doesn't that expression fit the bill in terms of being positive? Y minus 2 is positive if y is greater than 2, right? Y minus 2 is negative if y is less than 2, right? Agree? I'm not saying anything terribly profound here. So it stands to reason then, and here's a kind of a big idea, that if I set dy dx, right, equal to y minus 2, then solutions to this differential equation will satisfy this, because this is positive if y is greater than 2, it's negative if y is less than 2. So solutions to this differential equation will satisfy this geometric data, right? So you could directly engineer things you want from the solution by just crafting the right differential equation like this. Here's a simpler example. If I wanted, by the way, what's the solution to this? you can solve this by the integrating factor technique. What you'll get, I don't have time to show you the details, but the solution is y is equal to c e to the x minus 2. And so that solution is always either larger than 2 or less than 2, and it kind of trivially satisfies the conditions. They're either exponentials that, well, I'll shut up. These solutions actually have that. So my point to you is that we can think about the geometry we want for a solution set by just directly thinking about the differential equation itself. Like, here, one more example before I get to the punchline here. If I have dy dx equals to y squared, what could you say about the solutions to that just by looking at that equation? Or here, even this. Y squared plus x squared is what? It's a circle, if we set it equal to a constant. But just, I mean, in terms of just basic real number stuff, it's non-negative, right? So solutions to this differential equation, whatever they are, will be everywhere what? Everywhere increasing, right? They might be constant someplace possibly, but they certainly won't be anywhere decreasing, right? Solutions to this thing are always increasing. I can tell that from just looking at the differential equation. And I could figure out things about the concavity by taking the second derivative of this. I could look at like y prime prime is 2y, y prime plus 2x, and I could analyze that to answer questions about concave up and concave down directly at the level of the differential equation without even so much as finding a solution. We were able to say that. That's interesting. Okay, so that's just I'll get more into that if you take differential equations with me. Not much more, really. But the idea of orthogonal trajectories is much connected to this. So here's the idea. It's very simple. If you have dy dx equals to, say, m, and this is a function of x and y, let's say, right? This differential equation will have a family of functions as its solution set, right? For example, I think we worked this one out. Dy dx equals to minus x over y had we found solutions x squared plus y squared equals to r squared, basically, right? So those, of course, are this family of circles, right? That given differential equation has that family of solutions, right? This family of curves. An orthogonal set of, another family of curves, all right, which is perpendicular wherever it meets the given family, is said to be an orthogonal set of orthogonal trajectories. So you guys can tell me geometrically what those are from this, right? It's what? It's just these guys, right? Lines out from the origin meet the circles perpendicularly, right? If you look at the intersection point, the tangent lines are right angles, right? Agree? Now, how would you discover that in differential equations? For differential equations, you want what? You want dy dx for the orthogonal trajectory. For orthogonal trajectories, solve what? Dy dx equals to what? Not the original slope, but how do you find things that are perpendicular? What? Remember, if I have a line with slope 3, the perpendicular line has slope minus 1/3, right? So I do minus 1 over m. So as that applies to this problem, we would solve dy dx equals to minus 1 over minus x over y, which, by the way, is y over x. You separate variables, you got dy over y equals to dx over x. Integrate both sides. Natural log the absolute value of y equals natural log the absolute value of x plus some constant. Exponentiate both sides, you get absolute value of y is equal to e to the c times absolute value of x. But that just tells me that y is equal to plus or minus e to the c times x, which tells me y is equal to mx. Lo and behold, the lines. If you didn't understand every single thing I just said, it's okay. I want you to, the bigger picture here is to find orthogonal trajectories. You take the differential equation you're given and do minus the reciprocal. And that solutions to that will be orthogonal trajectories. This is super important because, for example, in a lot of physics, we look at orthogonal trajectories. For example, like in electrostatics, two-dimensional electrostatics, the places where you have equal voltage are called equipotentials. The lines which are perpendicular to those actually are field lines for the electric field. So the electric field is perpendicular to the equal voltage surfaces. And so this gives you a way of finding electric field lines from voltage lines or vice versa. Anyway, I shut up. Thank you. Have a good weekend. I expect lots of questions Monday. I hope.